we were discussing on inertial sensors. In my last lecture, I discussed different kinds of inertial sensors and their basic principles, mainly piezoresistive, capacitive and tunneling current accelerometers were discussed. Today, I will discuss in depth a specific accelerometer, how one can develop, starting from the design specifications, its analysis, layout generation and fabrication, and at the end testing. That we call it a case study. I have chosen a particular topic on which IIT Kharagpur has got strength, and we are working on that particular device last 2-3 years, and that is MEMS accelerometer for avionics. That means for space application, avionics application, we need some kind of accelerometers which has got certain specifications, not the same as accelerometers used for the entertainment electronics or say household appliance there, and those specifications are highlighted in this slide here, you can see, and it has been recorded from the data required for guiding an aeroplane, that is flight control system normal mode. So, for them a specific requirement is resolution, off axis sensitivity, temperature stability, linearity, etc. So, those points, how one can achieve those, I will discuss today, and the accelerometer which we are going to develop, that is based on piezoresistor mechanism, piezoresistor sensing mechanism, and it is used in aircraft. The range of that particular accelerometer is of the order of plus minus 13 G. Its resolution is 2 milli-G, natural frequency is greater than 100 Hertz. Full scale output is plus minus 6.5 volt DC. That has been taken from the accelerometer which are normally used in aircraft motion sensing. Those are bulk conventional accelerometer, that is why they need that much power supply. Obviously, if you go for MEMS accelerometer and if the whole control system is made with the modern electronics, obviously the 6.5 volt full scale output is not required, because nowadays most of the ASICs, either CMOS or bipolar, that is low voltage low power ICs are there if you go for CMOS application, so that people are working 1.2 volt power supply. Obviously, the output of the supply, output of the signal of the accelerometer in case of MEMS accelerometer may not be exactly 6.5 volt, may be different, but since people are using 6.5 volt supply for control electronics and other things, in case of conventional accelerometers, we will try to design that 6.5 volt DC output, but MEMS device output will not be that much, you have to amplify it to get that value. Linearity is 1% full scale, damping ratio is 0.7 plus minus 0.2. These are the specifications, and how to achieve that specification, how one will proceed to get those objectives, that is the topic of discussion today. Now, we are going to design a silicon micromachine piezoresistive accelerometer with low off axis sensitivity. What is off axis sensitivity I discussed in earlier classes, and low off axis means how much low. Particularly in case of aircraft motion sensing or avionics, if it is a one axis accelerometer, so off axis sensitivity should be extremely low, and that order should be at least third order low. So, sensitivity if your desired direction is, for example, if say 1%, then you have to go for 0.001% sensitivity in other two axes. So that is the normally third order is desired. If you get more than that, it is also highly accepted, but it should not be say one order difference. In that case, the along with the desired axis, other two axis sensitivity also will come into the picture. So those are the points, and those points we have kept in mind when we are going to design these accelerometers. Now you can see here the basic silicon piezoresistive accelerometer for this application is not as simple as possible, which I showed you a structure in last class, that is only two flexures, one probe mass is held by two flexures, and because of the acceleration the probe mass will go up and down, and accordingly the piezo resistance will change at the flexures. Now that particular design has got certain drawback, and the drawback is that is not highly stable, because the accelerometer which you are going to design, that has to survive with shock. One parameter is shock survivability. So for example, sudden shock or sudden jerk, the probe mass should not break away from the structure. For that reason, in this particular case we have used 4 flexures, not the 2 you can see in the figure. So there are 4 flexures, not the 2, and so here you can see that the 1, 2, 3, 4, and this is the probe mass and this is the beam, so that even with jerk or over acceleration the probe mass will not break, it will be stable. And if you say a cross section diagram along AB, it looks like this. So this is the probe mass here in the bottom diagram you can see here, and this is the flexure dimension, here is a flexure, and now if you, this is the flexure size and here is the flexure size where you are going to measure, going to fabricate the resistances. Now the equivalent model of the accelerometer is shown in this picture, where you can see a spring, and this is the mass, spring mass model, and if you give acceleration A, if mass is the, m is the probe mass weight, the acceleration is the force is equal to mass into acceleration m into A, which is equal to k dot x. K is the spring constant and x is the displacement. K dot x is equal to A into m, so obviously acceleration will be k dot x by m. That is the equivalent model of the particular accelerometer. Now if I go for the next slide, then you can see here the first job after finalizing the structure. So you have to have mesh it for stress analysis, because you are going for numerical techniques. So obviously finite element technique means you have to define small elements, which is known as a meshing. So meshing of the total structure is shown in this diagram, where you can see here the mesh size are not same throughout the structure. Why it will not be the same, that I also mentioned earlier, and the bottom figure shows the resistance part, and here the basically the diffuse resistance we are using. So the total resistance will be decided by the number of squares. If we know the width of this resistance and total length of the resistance, so we know how many squares are there, that is multiplied by sheet resistance will give you the total resistance. Now the two end of the resistance is having two bonding pads, contacts. So this two color is the two contact regions, and obviously if you metallize it, so or the contact must be at the middle of the resistance. So for alignment tolerance 10 micron each side we have allowed. So, if the dimension of the width of the resistance is 20 micron, so the edges will be 40 by 40 micrometer. Now, this resistance value is one parameter which you have to decide, and it will be limited by different requirements. So, if you use very long resistance, long length, width is large and length is long. So, in that case the problem is, the stress region is not very large. Maximum stress region, if you place the resistance, so obviously its sensitivity will be more and pickup signal will be more. So, that maximum stress region is not very large. So, over a limited region the maximum stress occurs. So, obviously the length or the size of the resistance should not go much beyond the maximum stress region. That is one limitation. And second limitation is that if you want to have very small resistance over the only centralized maximum stress region, in that case there is a fabrication tolerance is also there. If you go for say 2 micron or say 4 micron or say 5 micron width resistance, that is not possible. That means that is coming from technology limitation. So, keeping in mind of the technology limitation and the maximum stress region limitation, you have to decide the value of the resistance. At the same time, if you want to have large change over small stress, so the value of the R should not be very small. So, it depends on the value of the R. So, you are not going to fabricate 50 ohm 100 ohm resistance, at the same time you are not going to fabricate 10 mega ohm or 20 mega ohm resistance. It should be somewhere within few kilo ohms, so that the delta R is also large. It can be fabricated over a small region. And another thing is, seed resistance also depend on the doping concentration. The doping concentration side, the third limitation. You cannot choose any value of the doping concentration of the resistance. These kind of resistances are normally fabricated using boron doping, because we have seen that p-type silicon has got the piezoresistive coefficients larger value compared to the n-type. So, in that angle we will choose the p-type silicon in getting the piezo resistances. And not only that, in order to have the compatible technology with the VLSI fabrication, so it is better to choose resistances by p-type diffusion, because in VLSI most of the resistances are made not by n diffusion but by p diffusion. So, that is why along with the normal resistances in IC, if you want to fabricate the piezo resistance also in silicon, so we have to go for p-type silicon diffusion for getting the resistors. So, these are the various limitations, and with all the limitations keeping in mind, you have to select the geometry as well as doping concentration. Doping concentration limitation is because of various reasons. Some of the reasons I will highlight in today's lecture itself. Those are the variation of the piezoresistive coefficients and variation of the TCR with doping concentration. That point we have to consider when you are selecting a particular resistance. And another is, if that doping concentration is much different from the doping concentrations used for making resistances of integrated circuits, which are coming side by side if you go for smart sensor, that is also not desirable. So, these are the different limitations based on which you have to select the doping concentration, resistance geometries and values of the resistances. Now, this slide shows how a accelerometer, that means the structure what I have shown in the earlier diagram, looks like if it is facing an acceleration in z direction. And there you can see that this is the x, y and z, the directions. Now, Z direction is the vertically upward and downward, so it can go in this direction. Now, for 13G force, the proof mass will go downwards because of its inertia. So, as a result of which you have seen here the flexures, this is one flexures and this is another flexure, how the flexures will take the shape. And if you go for stress analysis, then the colored notation here shows the variation of the stress along the length of the flexure, and obviously the colored indication shows that maximum stress is this point. We are having maximum stress here, also this point is a maximum stress, here this point is a maximum, here also this point is a maximum. In the middle the color is same as the frame color, is a blue, so that is a zero stress. That means at the middle point there is no stress at all. The same thing is reflected in the right hand side diagram, where Mises stress is plotted across a distance. So, this analysis has been done using Coventer 2001.3 after meshing. So, now here you can see one thing, just accurately you can locate the maximum stress region. This is important to choose the location where the sensitivity is maximum, and you are going to place the piezo resistance in that particular location. So, now you see here Mises stress means it is a magnitude wise it is plotted over distance, and here is the stress component is shown in the bottom diagram, where it is shown positive and negative, because you can see here in this flexure near the frame end it is basically the stress are two kind of compressive strain and tensile stress. So, near the frame end is a tensile stress and near the mass end is a compressive stress. So, since elongation is something like that, so obviously it is like this. So, here the elongation will take place and here the compression will take place. So, now because of that you have seen here the where elongation takes place, this stress is positive and compressive stress is negative, is opposite in sign. Okay. Tensile stress and the compressive stress. So, one is positive or negative, but if you plot the magnitude wise, then is a Mises stress, it is known as, with distance flexure distance, flexure dimension is here 0 and this point is 1200 micrometer. So, this scale is 0 to 1200 micron. Now, we found this maximum point is very not at the 0, but very close to that, that is nearly the 70 or 75 micron is there in the next view graph. Similarly, here is a very close to the frame end, the maximum peak points are there. This is maximum peak region, this is the maximum stress, peak is here, means maximum stress is here, and here is the minimum. The same thing shows in the color diagram also, is a blue color here. So, now if we, the next view graph is the current also you can see, because depending on the change of resistance the current components also is going to change, that is a picoampere into 10 to the power minus 9. So, that you can see the current variation direction is also going to change if you localize the current simulation, if you do using the Coventer wire using a constant supply voltage. So, delta will change, if changes in positive direction then current will change some direction, and if it is a delta is negative direction the current may be in opposite direction, that is why you can see the current variation. Now, we found the maximum change in current or maximum delta R occurs at approximately the same points at which the maximum stresses on the beams were obtained. This is this point here, and another is another peak is here. So, these two peak is almost the same magnitude. Thus, the maximum delta R, the center of the resistors were placed at the maximum stress points, that is at an offset of 75 micron from the frame end and 70 micron from the mass end as determined from the stress curves. So, this is 75 microns here from the frame end and another is a 70 micron from the mass end is the probe mass end 70 micron. So I am telling, you can see this point may be the 75 here, this point is a 75 and this point is 70 micron from the frame end. So that is the maximum stress location. So now after finding that point, now you can place the resistances. Okay, the one job is over, where to keep the resistance. Now the complete structure, because as is mentioned in the requirement of the sensor specification, there is damping will be 0.7 plus minus 2, and at the same time you have the resonance frequency or the frequency is greater than 100 hertz. So those points are there. So obviously this kind of accelerometer will not be the bare, you have to have a top cap layer and bottom cap layer. So the total structure is shown here. So top cap layer is here, bottom is there, in between middle is a sensing element. So there the dimension were chosen now, and the sensor dimensions, again how do you select that? In this particular case, obviously the sensitivity also depends on the weight of the probe mass of the probe mass. So the mass has to be more, so that you will get higher sensitivity. At the same time, over the flexure there will be wearing. Wiring means if you make resistance, it has to be connected with some wear, so that the connections will come at the frame, from where you can apply the signal, and you can take the pick up the signal also, so that the metal lines will flow over the flexure width. So if flexure width is very small, so then again you cannot take out. So all these limitations keeping in mind, you have to design the flexure dimension, means length and width, and we have found in our application, depending on the technology limitation of our laboratory. So the flexure dimension was chosen 1200 micrometer, 250 micrometer and 20 micrometer. 20 micrometer is the thickness of the flexure, 250 micrometer is the width of the flexure, and 1200 micrometer is the length. If you go for 2-inch wafer, then its thickness is nearly 280 micron. So for 280 micron, if we take the probe mass size 3500 micrometer by 3500 micrometer, thickness is same 280 micrometer, then its weight is coming to be 7.5 milligram. Now this weight, if you want to make more and more, so sensitivity will be higher and higher. So this total sensitivity depends on prime two factors. One factor is mass of the probe mesh, other is the thickness of the flexure. So thickness of the flexure, here we assume 20 micron, but if you go below that, the problem is the handling of the piece wafers, because after making the center, the sensing element, top and bottom glass wafers or silicon wafers has to be substrate bonded. So that means some mechanical movement, the pressure has to be applied there. So because of that, if you go for very thin flexure, then the probe mass may break. So for that reason, you cannot go the 10 micron or 5 micron, although your laboratory can make the flexures very thin, but keeping in view of the handling of the wafers, bonding of the wafers, you cannot go very thin the flexures, and it depends on the technology available in your foundry. Okay. So for 20 micron, that is one parameter, another is probe mass. So probe mass weight you can go on increasing, and here we have used same as the substrate thickness, but you can increase more. How? By depositing some gold films on the probe mass. So if that is normally done by electroplating. If you electroplate gold on the particular the probe mass, the square probe mass which is used, so then although you are going to use 2-inch diameter wafer, so the thickness of the probe mass may increase by addition of gold layer over the probe mass. So these are the dimension we have chosen. Now resistor specifications we have used here 120 micron. 120 micron by 20 micron is the resistor dimension. Contact pad dimensions are taken 40 micron by 40 micron, because 20 micron is the width, 20 by 20 is the contact, and the pad should be 40 by 40, because it has to be aligned into the resistor, that is why 10 micron both side more, it comes to be 40 by 40. Resistor material we have chosen boron, seed resistance we have chosen 250 ohm per square, junction depth is 2.5 ohm, 2.5 micron, sorry, junction depth is 2.5 micron. Now this junction depth, one point is, if you go for stress analysis, so stress in case of silicon, we told you that it will be confined over the surface of the silicon, it will not go vertically deep into the silicon. Since it is confined to the surface, the stress region, so, and again we want to fabricate the resistor into the maximum stress region, so in that case junction depth limitation is also coming into the picture. And we will see in the next few slides, so junction depth, because you will see temperature coefficient or variation of the resistance also depends on the junction depth. So junction depth should be such that within that depth the stress variations is confined. Okay. If we make resistance well below that area where the stress variations is there, so its sensitivity will be low. So that is another point. And at the same thing you have to keep in mind, I told you it also many of the factors depends on the technology limitation of your foundry. But if I find in my simulation that the maximum stress region extend just below say 1.5 micron from the surface, but the 1.5 micron or 1 micron junction depth if I cannot make in the laboratory with confidence, with repeatability, so then I cannot make. See that normally if you go for ion implantation, so junction depth accuracy is much more compared to the diffusion techniques. So if you go for ion implantation technique for making the resistances, then obviously you can choose the junction depth as required by your stress analysis. Okay. Otherwise, if you go for diffusion, if you cannot control junction depth within 1 micron, then you have to go for higher junction depth. So you at the cost of little bit low sensitivity. So anyway, keeping all these factors in mind, we have chosen the resistance properties like this. Now the sensing mechanism, and next point we are going to address is the low off axis sensitivity. How can we achieve it? So now for that we have made two resistance on in each flexure. So simple piezoresistive piezoresistive accelerometer diagram which I showed in my last lecture, they contain one probe mass in two flexure and each flexure is having one resistances at the maximum stress region. But here in order to meet the specifications required by the avionics people, so here we have changed the structure little bit, and here we have made 4 flexures instead of 1, and each flexure is having 2 resistances. The total resistances will be 8. So 1, 2, 3, 4, 5, 6, 7, 8. So the resistances are shown here. You can see here is a one resistance, here is one resistance at the maximum the stress region, and now the basic principle is known, the resistance value will change due to the piezo resistance effect. Now the resistance values of the 4 resistance will increase and other 4 resistors will decrease due to positive and negative stress. Positive stress we call it as a tensile stress, and which is here you can see the positive stress. This is the region where you can see this is a positive stress region where plus delta R. So you can see the one flexure has been shown here with much amplification, the diagram. So here the bending of the resistance is like that, it's shown here. So automatically here is a plus delta R which is a tensile stress. Obviously in opposite side is a minus delta R because of the compressive stress. So that means each flexure the 2 resistance, one resistance is facing the tensile stress, other is facing the compressive stress. So if I make like this the total 8 resistance, so out of the 8, 4 resistance will increase, other 4 resistance will decrease. So now the change of the output, change of voltage at the Wheatstone's bridge output is proportional to the acceleration, and that is V naught is proportional to delta R, because delta R is proportional to acceleration. Now if I see this diagram, how you can get the off axis acceleration. Now you see, this is the again I have shown the sensing element where the 4 flexures are there, and I have named the 8 resistance by R1F, R2F, R3F, R3M, R4F, R4M. So now here you can see here, so now R1M and 3M are connected. M stands for mass end and F stands for flexure end. So you can see the opposite arms. So 1 and 3, the M are connected. In opposite to that, 2 and 4, the M are connected, mass end resistances. Similarly, other two side of the Wheatstone's bridge, the 1 and 3 here, 2 and 4. So 1 and 3 is here, 2 and 4 here. So 1 is the frame end, mass end, like that. Now if you look into the individual resistances, when delta R for x acceleration, delta R for y acceleration, delta R for z acceleration. Now under the no stress condition, if I make all the resistances are of same value, which is nearly 1.5 kilo ohm, in calculation or in fabrication it may vary a little bit, maybe say 1.3 to 1.5 kilo ohm, all the resistance are the same, then under no stress condition the total resistance value of each arm will be 3 kilo ohm if it is 1.5 kilo ohm per resistance, here 3, 3, 3, 3, so bridge is perfectly balanced. Okay. Now if you go for acceleration, for example z axis acceleration, the proof mass will take this shape. Now let us see how the resistances are going to change. Here for z axis acceleration you can see R1F which is here and R1M which is the mass end is here. So 1F plus delta, so 1F is increasing, 1M is minus delta, it is reducing for z axis. Similarly for second flexure R2F, all the frame end resistances are increasing, all the mass end resistances are decreasing, because all the frame ends are getting the tensile stress and mass end are getting the compressive stress. So in this way, so normally you can see if 1F and 1M are connected together, then there is no change. Similarly 2F and 2M are connected together, no change, it will remain same. So in that case you will not get any output. That means 1F and 1M in any arm of the bridge is not connected together. You can see 1M is connected to 3M. Similarly 2M is connected to the 4M. So 1M and 1F are not connected. In that case the total output will be 0. That we don't want. We have to get under z axis acceleration, V naught should have some value, but on x and y axis it should be 0. Now if I connect this in this fashion, then you can see for x axis, so where the first term we have 1M and 3M are connected, let us look, 1M has reducing and 3M is here, is increasing. So 3M is increasing, so 1M is reducing for this arm. So that means you can see if you add these two, this and this, one increases, one reduces, so automatically total value will be same, total change will be 0. Similarly you can see here 2M and 4M, 2M is increasing, this part you can see, and 4M is here, is reducing. So now if you add these two, so then you can see the total remains same, there is no change, isn't it? Similarly for y axis you can see here this is reducing and here this is increasing. Now if you add this and this together, so what is happening? It is also 0. One increases, another reduces. So in this fashion you will find that all the 4 arms, if you add like that, so total change delta will be 0 here and 0 here. On the other hand, if you add this and this together, so you can see here this is also going down, this is also going down. So total in this arm 2m and 4m, 2m and 4m connected here, 2m and connected is here. So this also reducing, this also reducing. So that means total delta R will be much more in this case in z axis acceleration, which is not same in x and y axis acceleration. Similarly here, if this total reduces and this total will increase in case of z axis. So in this way, if you connect judiciously these 8 resistances, we found that in particular direction of acceleration, the maximum output will be obtained. For other x and y direction acceleration, the resistance increase or decrease cancels each other, so that in those two directions you will not get any voltage or maybe very negligible amount of voltage, you can, so that you can get very high off axis sensitivity. Now if you look in the next diagram, so what I just told you, it's shown here. For this is for x and y axis acceleration. So in x and y axis acceleration you can find here. So you can see this each arm I have shown by arrow increasing and decreasing. So here you can see this is under x axis acceleration, this is along the x axis, this is along y axis acceleration, they are perpendicular each other. So along x axis the proof mass will take this shape. So this is along x axis, it's shown here. So a proof mass will take this shape. So now here in each arm, from that table I have drawn the diagram here. So one increases, another decreases, here this increases, this is going to decrease, here this increases, this is reducing, increases, reducing, like that. So that means the total delta change will be 0 in this case. Similarly here also you can see this increases is opposite, is reducing, and this is also increasing. So total change is 0, here is also 0, here is also 0, here is also 0. So x and y axis acceleration you should not get any output. Now if we summarize that, we can say to achieve low off axis sensitivity, that two frame end or mass end resistances for each branch are paired such that if one increases the other decreases, so as to keep the bridge still almost balanced. And here is shown how the 1f and 3f going in up and going down, 1m and 3m, 4f and 2f, and 4m and 2m, those are connected in pair and that is fixed in each arm. So if the resistance are paired like this, we can achieve very low off axis sensitivity. Now this is okay. Next point is I have to go for designing that the frequency should be greater than 100 hertz, the natural frequency. So for that we have to do some modal analysis, because any structure, if you do the modal analysis, it will go for the first mode, second mode, third mode, like that. So that modal frequency, the frequency versus response, if you plot, so there will be at the resonance frequency the maximum output will get, but we don't want to resonate the complete structure, so that may create problem to the total device. So we should, because we know our devices are all DC and very low frequency signals are there in those sensors, so that the resonant frequency of the complete structure mechanical analysis if we do, so that for different mode we have to see whether it is below 100 hertz. That we have done using, that is normally obtained from modal analysis using Coventer wire. So z direction, y direction, x direction, the frequency frequency versus the signal output or the magnitude of the displacement, all the things is plotted here, and we found there in all cases the frequency of is well above the 100 hertz. So now if I see for mode 1, the modal frequency is 1.65 kilohertz, for mode 2 it is 2.83 kilohertz, for mode 3 it is 4.01 kilohertz. That means our specification should be greater than the natural frequency is near 100 hertz, and our design should be, it should be greater than 100 hertz. So in all cases it is well above 100 hertz. So that specification is meeting. So that means in that, so far the natural frequency is concerned, this structure satisfies this specification. Now, the next point is the simulation, where you can see how much the value of the resistance are going to change. So, now for here you can see the R1F, 1M, 2F, 2M, 3F, 3M, 4F and 4M. So, each resistance, so it is a no stress value is 1357.19 ohm after the doping and other things is decided, junction depth is decided. So, it was like that 1.357. So, this resistance are shown here, and delta R the change of resistance for 13G acceleration, that is also calculated, and those values are shown. Delta R is, you see, one is plus, another is negative, plus minus, plus minus, plus minus. It stands for one for tensile, another for compressive. So, tensile is the positive and the other one is negative, is for compressive. So, is another parameter. Another parameter is basically delta R by R. So, delta R by R here you can see. So, this is a delta R 5.682 divided by 1357.2 ohm. So, it is coming nearly 4.186 into 10 to the power minus 3. So, now if you critically analyze the result, you will find that 1F, 2F, 3F and 4F all are 4.186, 4.186, 4.186, 4.186 into 10 to the minus 3. On the other hand, the 1M, 2M is a 4.054, 4.054, 4.054, 4.054. So, that means all the resistance are change are in the compressive and the tensile, one is increases and decreases are in the same magnitude. Okay. That means this total structure shows a uniform variation. That means we found here all the frame end resistance will increase, while all mass end resistance will decrease. Okay. Now, next table, next slide shows the output of the simulation. The output voltage V naught for that delta R by R change. So, total output voltage is how much? Delta R by R into Vs. Vs is the supply voltage. So, if you apply Vs 4 volt or 5 volts, so then the bridge voltage we found is nearly, it's coming 20.6 millivolt, and the mean delta R by R is 4.186 10 to the power minus 3. Sensitivity was calculated to be 81.75 ppm per G. This is the Z axis sensitivity. The displacement of the probe mass was found 5.17 micrometer. Displacement means from no stress to 13G stress. So, that means the probe mass will go down from the rest position 5.17 micrometer only for 13G, and you will get 20.6 millivolt output if we supply the bridge voltage 5 volt. So, now this is x axis, the earlier table is for z axis. For x axis, the simulated result shows that the stresses were found to be 0.43 megapascal for the probe mass side and minus 0.43 megapascal for the frame end side. The distance of the peak from probe mass end is found to be 30 micrometer and 33.63 micrometer from the frame end. So, these 2 points here and here, in earlier case was 70 and 75 in z axis, but for x axis it is nearly 30 micron and this is 33 micron, the maximum peak points, peak stress regions. And the resistance values here also calculated for x axis acceleration. There we found, you can see the 1F is minus 3029 and the 1M is plus 2.777. So, delta R by R value you can see 2.232 for 1F, 2F, 3F, 2.223 and the 4F 2.323. You can see here slight, all are not same. Here is 2.046, here you are getting 2.062, here you are getting 2.062, here 2.046. So slight variation is there, even which is increasing and which is reducing, same value is not there in all arm. So because of that, the sensitivity, off-axis sensitivity will not be exactly 0, but some value will get, because of the in a third decimal place some variation. So now we found the bridge output at 13G in x-axis is 0.97 microvolt, which you got in z-axis is 20 millivolt, but here in that you will get only 0.97 microvolt, accounting to 0.0746 ppm per G, which in earlier case how much? The sensitivity is 81 ppm per G. You can see here 81 ppm per G, which is coming down here the 0.0746 ppm per G. That is the sensitivity, which is about 0.004% of the z-axis sensitivity. Okay. Here proof mass displacement is found to be 0.047 micrometer. In earlier case nearly 5 micrometer in z-axis, but in x-axis the displacement is very small and the sensitivity is 0.0047% of z-axis. So that means, as I told you, for this the avionics application, the off-axis sensitivity, if you need for one axis design, off-axis should be low and is a third order. So it is really you are getting the variation is a third order variation compared to the z-axis acceleration. Now let us see now in y-axis. If acceleration is subjected in y-axis acceleration, in that case again the similar analysis we carried out just like z-axis, and there we found the stress is found to be 1 megapascal for the proof mass side and -1 megapascal for the frame side. The distance of the peak stress from the proof mass end and from the frame end are respectively 30 micrometer and 33 micrometer. That is shown in this point here. This is the peak and here is the peak point, that is nearly that, and along the y-axis the shape of the structure looks like this. If you push in this direction, is y-axis is here, and in this direction if you push it, the proof mass will take this shape, and as a result of which the resistance change will be like this. Here you can see some important points, so that the change of resistances or delta R by R value is not exactly same in all cases, and you find in a third order and second decimal point is varying. So 8 point, you can see here the 8 point, this is 1F is 4.854, 4.854, here is 4.865 and here is 4.865. Similarly other is 4.850 is the M mass end, here is 4.887 and another mass end is 4.887. So because of that little bit variation, you will get some sensitivity in the y-axis, and bridge output is 13G, y-axis in y-axis is 3.257 microvolt. In earlier case you got how much is a 0.97 microvolt along the x-axis, and here you are getting little bit more than that, that is 0.97, 3.2, here amounting to 0.251 ppm per G is the sensitivity, which is about 0.0158% of z-axis sensitivity. That means the x-axis, the off-axis sensitivity is much low compared to the y-axis. Here you are getting second order 0.01, and in earlier x-axis you got 0.00 something, isn't it? That means here the y-axis sensitivity is not that much what we expected, although it is very low compared to z-axis sensitivity, but still it is not like the x-axis. So for that you can have some design modification, and that modification if you do, then you can get both x and y-axis, the sensitivity is again third order less compared to z. And what we did there, the flexure what is shown here, you can see the flexures here is not at the edges. This is the proof mass, you can see the proof mass, and if you make the flexure at the edge here, this point and this point, then it will be improved. And you see this diagram, in the right side diagram, the flex charge is not in between the edges, but at the edges. So, you can see here is at the edges you have made the flexure, this edge you have made the flexure. So, if you do like that, again you go for the complete analysis, that will not change your z axis acceleration value, but x axis and y axis output voltage will again drastically low, and sensitivity will further improve if we put the flexures at just edge of the probe mass. And that we have done again the same simulation, and then we found the results are also encouraging. And here in a similar way we did the model analysis. In the model analysis I can found that, see, the 1.65 kilohertz is the frequency here resonance, and the second is a 2.83, and here is the 4.01. So, not much change of that model analysis because of the movement of the flexure. But here the change of resistance values for Z acceleration, no load stays here is 1.5 kilo ohm, and here the resistances are 1F, 1M, all the same kind of location we have used, and there you can see the values delta R by R. You can see 3.892 here in 3.892, 3.892, 3.892 for frame end, and all the mass end is 3.766, 3.766 here, 2M, 3M is 3.766, here is 3.766. So, this is all uniform change, and if you go for the output simulation, we got here this output voltage V naught of Wheaton's bridge is 19.15 millivolt. In earlier we got nearly 20 millivolt. So far the Z axis acceleration is concerned, the output voltage is not going to change at all, model frequency is not going to change at all. Bridge supply current here is again 1.6 milliampere or 5 volt, and probe mass displacement here is different, 1.18 micron, where in earlier case nearly 3 to 5 micron. Although the probe mass displacement is different, but the output voltage is coming almost very close to that. That means so far output is concerned, it will not change at all. But if you look into this result, what is result? There is off axis acceleration result. So, lot of improvement has taken place. So, here the output in this particular case is 19.15 millivolt, and part G, this is for all 13G. So, part G it is coming 1.47 millivolt per G, x axis is 1.22 microvolt total output. So, part G you are getting 0.0938, and in y axis 0.075. So, if you calculate the off axis sensitivity, you can see here for x axis you can get is 0.0064% of the z axis output, here 0.0032% of the z axis output. So, all are third order change you are getting. So, that means the so far off axis sensitivity is concerned. So, if you shift the flexure at the edges, so improvement has taken place. So, for only for off axis sensitivity is concerned, but there is no change z axis, and here probe mass displacement here is 1.18, 0.047 and 0.092 micrometer. So, this kind of design may improve the off axis, and the complete calculation of the output voltage with G has been done, and that plot is shown here for bridge supply voltage of 5 volt, and here you can see from 0 to 13 volt we have calculated the output voltage. At 13 volt I told you in earlier diagram also shown is a 19.6 or 7 some volt millivolt you will get it, and for different G value the output voltage has been calculated from the change of delta R by R, and the plot is shown here is exactly linear. That is one of the requirement of any kind of this sensor, the performance is highly linear. So, from along z axis acceleration is highly linear, and the value is in the order of millivolt, and that you have to connect some amplifier to get it in volt order. Now, so far an x and y axis is concerned, acceleration is concerned, you can see here the scale, you can see it is a millivolt, but it is 10 to the power minus 3, that is in microvolt order. And again this x and y is not as linear as obtained in z axis, that we do not we want this value should be as minimum. Is you see compared to z, it is a third order less output voltage, and that variation up from 0 to 13G is plotted in this curve. Now, that means at the end of this design, another parameter we discussed here, that is linearity. So, linearity is another point which we want is it should be linear, it should be 1% linearity. So, there the linearity can be calculated from endpoint fit method. So, here is the how we can go for calculating the linearity value. So, this is say a plot versus input is a P is a input variation and is output is always you want the voltage variation. So, P naught to PR is the change, here V naught to VR is this is arbitrary some curve, V naught to VR is the output, P naught to PR is a input change. So, your ideal characteristics is linear, which is shown by the dotted line, but your real curve which is obtained from the experiment or simulation may be like the solid curve. So, solid curve and dotted curve has got certain deviation. Okay. So, that deviation, how much deviation? So, that is basically the linearity, and it is calculated by the relation. The linearity L is given by, so any point at the middle where the maximum separation is there, that is the maximum deviation. So, that point you select as Z point here. So, that voltage Vz here for an input Pz. So, for an input Pz, if you get the output Vz, so now this if you calculate like that, Vz minus V0, V0 is here, divided by Vr, Vr is the endpoint, one endpoint is Vr, that's why endpoint fit method is called. Two endpoint values are taken, V0 and Vr. So, then Vr minus V0 minus Pz by minus P naught divided by Pr minus P0. If you calculate this value, this is called the linearity, and the linearity as calculated by the endpoint fit method from our design, our curve is this curve, Z axis acceleration, which I just the earlier plot has been repeated here. So, acceleration versus the output voltage. So, this curve linearity was found to be 0.16% of the full scale. Our design is 1% of the full scale. So, we are getting far less than our design our expected value. So, in that way, so far the linearity is concerned, we are satisfying our specification. Off axis we are satisfying our specification, and the linearity off axis the model frequency analysis we are satisfying the natural frequency. So, those three things has been done in our simulation, and let me stop now. So, in the next lecture I will do other two parameters which are also very important, damping and the temperature drift or temperature variation from the piezoresistive sensors. Okay. Thank you very much.